In this video, I want to cover the concept of linear regression, specifically as it relates to the computer system measurement of G laboratory, to give you an idea of how you set up a linear regression from scratch without using some internally available code or something within a program, a spreadsheet, or whatever. I think this is instructive because then you'll understand how in the world do they generate these fits to the data and how good it is and so forth like that. Now, the specific case we had here is the one where you drop the picket fence down through the photo gate and obtain data. Now, the data I obtained is here in the first column. It's a set of 7 numbers over here, if I can select it. And that set of numbers are actually what was spit out by the photo gate. I actually ran it in photo gate mode as opposed to photo gate with the picket fence because I wanted the actual times when the lines passed. You can use the other data as well, what comes from the description within the lab write-up. You'll get the same type of results. Now the whole process is now you have to convert this because we just have times, but we have to convert those times into a time and a average velocity as described in the lab write-up. And that's what's done in the rest of these columns here. So notice this was my input, time in, delta t, the midpoint timer, that average time within the bin, and the average velocity associated with it. I have one other number over here that I'll keep for later, and that is the distance between the different dark lines in the picket fence, the 5 centimeters, written in meters because I want to get units at the end in meters per second for the velocity. Now, a simple process here, I just put in formulas in the spreadsheet. Here's A3 minus A2, that's the change in time, the delta t, and I bring that on down and fill up all my columns, or all the cells within the column. The midpoint time is just the average, A2 plus A3 divided by 2, and set those up. So here are the delta t and the midpoint time as described in the write-up, taken directly from the data. That's then used to find an average velocity by dividing the distance by the time. Now notice there's some things here that we want to deal with. First of all, notice that the time gets shorter, delta t gets shorter. Well, that makes sense because it's moving faster. It takes less time to cover that distance. The time here, midpoint time, keeps on increasing in a nice, smooth manner. Now, if that's not the behavior you see, you probably messed up a formula somewhere. Next thing, when I use something like this, as opposed to putting this number into each formula, I like to set it up in a cell within the spreadsheet because I can change that. Let's say I did a different one, but I could do the same thing with a different spacing between the photo gates. I could just change this one number and redo everything. But when you do that, you have to use this $ symbol to lock in the position. So $F, $1 means fix column F, fix line 1 or row 1 as being where you're going to call it from. And when you copy that into the different cells or pull it down, you're going to get the right value. Now, this is my data then. I have a time and a velocity which I want to fit. Now I can plot that, and that's what I've done down here at the bottom. I've plotted the data points. They're kind of blue dots there. They're very small. This plot actually includes the fit, which I'll describe later. And if you see here on these data points, there's little black lines. Those are actually the error bars for that, and I'll have to explain later where I got the error bars from. Because right now, I don't know the uncertainty in this average velocity, and I don't have an uncertainty associated with the time, so I'll get that later. But the idea is now is to take these two sets of data, the x and y, or velocity and time, and fit them. Now to do that, I'm going to move over here a little bit further in my spreadsheet, and I'll explain how I did that. I set up cells here with x and y and just copied over the data. I do it associated by cells because if I find out later I made a mistake, hey, it's easier to just reference a cell where I make the correction than it is to copy, actually paste in the data. Now, to do the fit, I have to understand what I need for the fit. So I want to look over here at this side at these formulas. Sorry, I got something highlighted there. These formulas are from the last page of the write-up on simple data analysis, which shows you how to do an unweighted linear least squared fit. And it says the fit parameters, in this case y is equal to a1 plus a2 times x. So these are the two fit parameters, a1 and a2, and they're determined by these formulas out here. But let's look at the composition of the formulas. Notice that you have a sum of x squared, a sum of y, sum of x times y. Just some simple things, simple sums that we can set up. Now, I need a sum of x, so I've set up all my x values, and I just do a sum. So if you look at the top column here, it's a sum. Now, I actually set this thing up to sum over a larger range than I needed, but that's fine, because if I want to add data points in here or use this for different fitting a different set of data, I can, because once I set this up once and I have it working once, no reason to recreate it. I can just use the same spreadsheet again, as long as I have the right sum up all the data points. In fact, you could remove data points, lines in here, and not have a problem in it. So the top line here is the sum of what's in that column. So here's x, here's the sum of y. The other things I need, something like sum of x squared here, which means I need to calculate x squared. So that's all I did in this column, x squared. And over here's x times y. And that's all of them we have. It's just, if you look at the equation over here, there's not a whole lot of sums. There's only those four sums you need. Sum of x, sum of y, sum of x squared, sum of x times y. You also need to have the value of n, the number of data points. Now you say, well, I can just count those up. That's easy. That's 6. Well, I still like to use the count function. Let me show that here, to indicate how many data points I have, because I can do the count over the same number of columns, and it counts up only non-zero cells. So if I want to remove a data point, there's a data point that's obviously bad, and I just want to remove it, I can do that without having to change anything. It's automatically going to update within the fit. Now I just have to set up some other things. One is delta. Delta is given by this equation, n times the sum of x squared minus the sum of x quantity squared. So I just do that as a formula here. If you look at this, it has the sum of x, which is, I get the right one, sum of x, I'm doing this wrong, sum of x squared, which is J1, times n, which is L1, so that's n times sum of x squared minus sum of x quantity squared. Sorry, had trouble reading my own formula there. And that gets me delta. Now, why is delta important? Well, because delta is required by both of these formulas for the two fit parameters, a1 and a2. And then I just have to set up the values for a1 and a2, doing the similar thing. I'm going to do these sums and just pick them out. So if I go over here, click on the right cell, this is sum of x squared, which is J1, times sum of y, which is I1, which is what I have there, minus sum of x, which is H1, and sum of xy, which is K1. And then I divide it, if you look here, divide by O3, which is delta. I do the same thing with A2. Just follow the formula exactly, type it in here, and you'll have the right result. So notice now we have our intercept and our slope. And these are the values from the fit. And I can actually calculate that from a fit. Now, so notice here, I haven't explained all the columns I have here, because the next one here is what I call y-fit. That is simply an equation which takes the two fit parameters, and again I use absolute locations for those two parameters and multiply by x, and that gives me the value from the fit for y. And I did that for each of the points, each x value, and that's how I got this line, the red line over here in the plot. Let me scoot over there. So, and you see it goes through the data points quite well. Very nice looking. That's because we have a very solid theory from physics as to what's going on, and so it should be a linear relationship. The other thing we need to do is to calculate the uncertainties. If you look down here, the uncertainties in A1 and A2 both have a quantity sigma y. And that sigma y comes from this equation up here, which requires me to know the difference between the fit value and the measured value. Y sub I is the measured value, so like 1.2 2077, and y-xi over here, that's the calculated value, that's 1.2101. So that's why I call it. In this column over here, which I call delta, that is just the calculation I've done, the square of the difference between the two. Do that for all the points and sum them up at the top of the column. So why do I use the sum? Well, because here the sum of that difference. So I've summed that out. I now need to divide by n minus 2. And that's what I'm going to do here. Here's my sigma y, which is given by the square root. Again, I'm taking the square root of this, of the sum, and the sum is m1. That's up here. And, sorry, before I mess up my formula. I don't know, there. Sum of m1 divided by L1 minus 2, so that's 6 minus 2. And it gives me the right result. Now this value, what's sigma y? Well, when I started, I said I didn't know anything about what the uncertainties were in my y values, my average velocities. Well, this, based on statistical analysis, is the uncertainty in those average velocities. And that is the value I use to specify these little error bars over here on the data points. So you notice the data points are actually pretty well known. I mean, the uncertainty there is fairly small when you look at it. So that's how I came up with this value. I then go down to my formulas and just calculate the uncertainties in A1 and A2, putting them in here, just following the formulas as they're written, and I get the values. So now what we have in the end is we have measured a value of G of 9.81. That's my value, with an uncertainty of 0.05. And that sounds like a pretty good result. Sorry, my mouse is not clicking on things. So 9.81 plus or minus 0.05 meters per second squared would be my answer for this one measurement. And if I go in and look at what comes out of Data Studio, when it calculates it, it should come up with the same value, telling me that it's done that calculation correctly. So I hope this helps you in setting up a simple linear regression. The same idea of what I've done here and how I've set up my columns can be done for any linear regression fit. So I would suggest, if you're ever going to do many of these, go ahead and set up a spreadsheet that has it, and it will be done for you. That's all for right now.